Hello everyone, myself Dr. Kouser, Assistant Professor of Computer Science. Welcome you all to Session 4 of System Software and Operating Systems course. The Session 4 is on Introduction to Assemblers. We have come across the term assemblers in the previous semesters when we learnt about different types of languages and the translators used to convert one language to the machine level language. So let us see what an assembler is. An assembler is a program that accepts a symbolic language and produces its binary machine language equivalent. So these assemblers are central to the use of any machine when you are using a symbolic language, or it is also called the intermediate level language. An assembler is the translator that converts the symbolic language and produces its binary machine language equivalent. And we know that computer understands only the language of zeros and ones, also called the binary machine level language. Here the input to the assembler is the input symbolic program, which is the source program, and the resulting binary program is the object program. So before we understand the working of assembler, we should know in detail about what a assembly level language is. Each personal computer has a microprocessor that manages the computer's arithmetic, logical and control activities. An ALL or assembly level language is a low level programming language for microprocessors and other programmable devices. ALL is higher than machine language but lower than the high level language. A processor understands only machine language instructions, which are strings of ones and zeros, like I already mentioned. However, machine language is too obscure and complex for using in software development, so the low-level language is designed for a specific family of processors that represents various instructions in symbolic code and a more understandable form. To simplify the program writing process used in machine language, the numeric operation codes of machine language were substituted by letter symbols, also called as mnemonics. The language which substitutes letters and symbols for the numbers in the machine language program is called an assembly language or symbolic language. ALL is defined by set of rules. User must conform to all format rules of language if they want their program to be translated correctly. Basic unit of assembly language program is a line of code. So let us see the rules of assembly level language. So each line of assembly language program is arranged in 3 columns called fields, and the first column is the label field, which may be empty or specify a symbolic address. The second field is the instruction field, which specifies a machine instruction or pseudo instruction. The third field is the comment field, which may be empty or it may include a comment. In these 3 columns, the important column is the instruction field, which has to be present, and the label field along with the comment field is optional. See the example here. Lab add op1 / this is add operation. Here lab is the label field. Add op1 or operand 1 is the instruction field. / this is an add operation is the comment. So here you should note that lab is the symbolic address. First, let us understand what symbolic address is, and then we also learn about these various fields, the label field, the instruction field, and also the comment field. Symbolic address consists of 1, 2 or 3 alphanumeric characters. The maximum alphanumeric characters that can be present in a symbolic address is 3. Here the first character must be a letter. The next 2 may be letters or numerals. A symbolic address in the label field is terminated by a comma so that it will be recognized as a label by the assembler. So you can see the comma here next to lab. So that helps the assembler understand that lab is a symbolic address. A defined symbolic address must occur again in a label field. So these are the instructions for the symbolic address, which should be followed in an assembly level language. So coming to the instruction field, so the instruction field can be one of these three instructions. The first one is the memory reference instruction. The second is the register reference or input output instruction, also called the non-MRI. The third is the pseudo instruction, which can be with or without an operand. First, let us understand the first type of instruction, that is the memory reference instruction. This memory reference instruction occupies two or three symbols separated by spaces. The first must be a three-letter symbol defining an MRI operation code. For example, ADD add is a memory reference instruction. The second is a symbolic address. So you can see an example here. Add OPR is a direct address of MRI type. And the third optional letter I, if it is used, it denotes that it is an indirect address instruction. The same example, if you add an I at the end of it, then that refers to that instruction as an indirect address of MRI. A symbolic address in the instruction field specifies the memory location of the operand. This location must be defined somewhere in the program by appearing again as a label in the first column. Example, LDA X1. So this tells about the load instruction into the accumulator A, and X1 is the operation to be performed. So coming to another type of instruction, that is the non-memory reference instruction, called non-MRI in short. This instruction does not have an address part, that is why it is called the non-MRI instruction, and it is recognized in the instruction field by one of the three-letter symbols. It can be CLA, INC or CLE. Coming to the third type of instruction, that is the pseudo instruction. The name itself tells if it is a pseudo instruction, it is not a machine instruction. It is an instruction to the assembler giving information about some phase of the translation. So this gives important information about the phase of translation. A defined symbolic address must occur again in a label field. A pseudo instruction is an instruction for the assembler and it gives information for the translation phase. So this pseudo instruction is very important for the translation phase. So here I have listed few pseudo instructions. The first example is ORGN. This ORGN is a hexadecimal number. N is the memory location for the instruction or operand listed in the following line. The other instruction is END instruction, which denotes the end of a symbolic program. The next pseudo instruction we'll learn about is DEC of N. DEC stands for the signed decimal number N, which has to be converted to binary. Similarly, we have HEX of N, which stands for hexadecimal number N, which has to be converted to binary. These are the four pseudo instructions which are popularly used. Coming to the last field of assembly level language, that is the comment field. A line of code may or may not have a comment, as already mentioned earlier. See this example, STAA0 / storing at A0. This slash indicates the beginning of the comment field. That is, a comment must be preceded by a slash for the assembler to recognize the beginning of the comment field. So now that we have understood about the rules of the assembly level language, now we move on to the next topic of this session, that is the address symbol table. Address symbol table helps in the translation process, which can be simplified if we can scan the entire symbolic program twice. The translation program is simplified if we can scan the entire program twice. But no translation occurs during the first scan of the translation phase. We just assign a memory location to each instruction and operand in the first scan. Such assignment defines the address value of labels and facilitates the translation during the second scan. Actual translation occurs in the second scan. We cannot assign a numerical location for pseudo instructions because they do not represent an instruction or operand. So this is about address symbol table. Now we move on to the next topic, that is representation of symbolic program in memory. User types the symbolic program on a terminal. Then a loader program is used to input the characters of the symbolic program into memory. Since user inputs symbols, program's representation in memory uses alphanumeric characters, which is an 8-bit ASCII. The input for assembler program is the user's symbolic language program, which is in ASCII. This input is scanned twice, like I mentioned earlier, to produce the binary equivalent program. A line of code is stored in consecutive memory locations with two 8-bit characters in each location. That is, we have 16-bit wide memory available. A line of code is stored in consecutive memory locations with two characters in each location, and this end of line is recognized by the CR code. That is the code assigned for a particular character. Here is a list of codes which are used for hexadecimal characters. A is represented by 41, B by 42, and so on. And once you reach 49, it is not, you should observe that for J it is not 50 but 4A, because we are using the hexadecimal code here. After 9, the codes that we go on to use is A to F, and again it starts with 0. So J has 4A, then O has 4F. So when you have represented the codes from 1 to F, then we go back to 0. So P is represented by 50. Similarly, you have various codes for other characters till Z. Then 0 is represented by the code 30, and 9 is represented by 39, and for various special symbols we have specific characters here. So CR stands for the carriage return. In this figure 4.2, we have an example where a line of code PL3 LDA sub I is stored in 7 consecutive memory locations. Here you have the memory locations or the word. We have already learned that one word is equal to 3 bytes, which is equal to 24 bits. Here the first word has symbols P and L, and its equivalent hexadecimal code 50 and 4C. You can see the symbols here in the previous table. L is 4C and P is 50. So same representation is given here for PL3. And the binary representation for 5 is, we know, 0101. 0 is represented in binary using 4 bits as 0000, 4 as 0100, and C is represented as 1100, which is nothing but 12. 8 plus 4, which is 12. In the hexadecimal, for 12 the representation is C. Similarly, for the number 3, the equivalent code, hexadecimal character code for 3 is 33 here. So that representation is given, and the special symbol comma is represented as 2C, and that representation is given here. And similarly for LDA and sub I, the symbols are represented with its equivalent hexadecimal codes from this figure below, figure 4.1 above. So with this example, we understand how the memory words and the symbols are represented using hexadecimal code and then given its equivalent binary representation. So with this, we come to the end of session 4. In this session, we have learnt about what assemblers are, an introduction to assemblers. Then while understanding assemblers, we also learnt about the assembly level language and what are the different rules of assembly language, followed by understanding of address symbol table in brief, and also the representation of symbolic program in memory with this example here. In the next session, we learn about first pass of assemblers. And the major tasks performed by this assembler are first pass and second pass. And whatever the preliminary or introductory part necessary for understanding the first and second pass of assemblers is presented in this session 4. Thank you all for your patient listening.